Hey Astronomy kids, we want to go over question 13 today, which is draw an HR diagram. Now what's an HR diagram? The HR stands for Hertzsprung-Russell. These were the two scientists who came up with this diagram, and this is almost certainly the most important diagram in all of astronomy. This explains how stars work. We started seeing some things and we put it together in a brilliant way, and now we could talk stars on basically how they live their normal lives and then how they die, all based on this diagram. So it's an important diagram to understand. First thing we have to get out of the way is, how do we figure out the brightness of a star? I mean, I look at our sun and it looks like the brightest star in the sky. You know that's because it's closest. Some stars that are intrinsically very, very bright look dim because they're really far away. So astronomers have a way of handling this. They mathematically calculate the distance to the stars and then how bright that star would be at a particular distance from us. Now they use the distance of 10 parsecs because that's a directly measurable quality of stars. So 10 parsecs is 32.6 light years. So just take every star in the sky and move it 32.6 light years away, and now how bright are they? And that is what we plot up on this axis. If we move all the stars the same distance, we can talk absolute luminosity. The absolute luminosity. Bright is up here, and dim is down here. Now across the bottom axis, took a really long time to figure this out. We basically need to know the temperature of the stars. Now how we do that, we look at the spectrum of the stars, and we've spent the last more than a century working very hard to understand spectra of elements. What do they look like when you heat them up an awful lot? What's a star's spectra going to be like? It turned out we got it wrong when we first did it. We did A, B, C, D, thinking that that was in some sort of order. What we find out now is that's how it works out. O, B, A, F, G, K, M. Do you really need to worry about that? Well, the key is simply this. Down here, the stars are cool, and over on this side, the stars are hot. That's the key. And that's what the spectra is telling us, hot and cool. So let's think about this. If you have an intrinsically really hot star, is it going to be brighter or dimmer than the other stars if you move them all to the same distance? I would think if I take a light bulb and I make it really hot, it's going to get brighter. If I make it really if I make it really cool, it's going to get dimmer. So what I would say, and I think you would too, is that we have the cooler stars down here, and we have the hotter stars up here, and the stars in the middle are sort of like that, right? So saying the cool stars are dim, right? Dim. So the cool stars are dim, the hot stars are bright. And in fact, this is exactly what we find when we look at stars and analyze the data carefully. So we have a name for this large grouping of stars. This group is called the main sequence. And the main sequence is where 90% of the stars in the sky are. They are calm, peaceful, living their lives, and you can tell that by stellar theory says they're burning hydrogen into helium, fusing it in the core using the strong force to release enormous amounts of energy as they take hydrogen protons and slam them together and make a slightly lower mass helium nucleus, and a slight loss in mass, E equals mc squared, turns to tremendous amounts of energy. That's why stars shine. So they're placed along the main sequence. Now let's talk about stars on the main sequence. We'll just kind of itemize here, in the center, and then in the bottom corner. So up here, stars are very bright, they're very hot. How do they do that? Well, they're so big, there's so much mass there, they're pressing into the center so hard that they cause the nuclear reactions to move at a fantastic rate, even though these are huge, massive stars, right? So the star here, it has high mass, and even though it has huge mass, it has a very short life. And everything else you can tell. It's blue and it burns very, very bright. High mass means short life. When they die explosively. Supernovas, leaving either neutron stars or black holes. These are amazing stars. Now, you and I owe our existence to these stars because in their death throes, they made all the elements necessary for life. The lower mass stars make some of the elements, but the high mass stars make pretty much all the elements. We understand there's some stellar processes like neutron star collisions that may make a proportion of the elements we use, but the supernovas make a lot of the stuff that made up this Earth. The Earth is not just made of hydrogen gas. The only place you could have gotten this other stuff that Earth is made of, supernova. Okay, down here, a middle star. Hey, like our sun, it's in the middle of everything. It's a medium mass and a medium life. Well, now the numbers are all over the place because this is a really wide range, but how about talk about our star? 10 billion years is about its life. What about these? It might be 10 million years. They might die in 10 million years. Anytime you see a picture of a galaxy and you see a picture of an arm of the galaxy and there's a bunch of blue stars there, that has to be a place where star formation is going on right now. These things take so long that 10 million years is a very short time to live. So if you still see blue stars there, stars must be forming basically right now. Our sun is a yellowish star. It lasts for 10 billion years. If you see a cloud of yellowish stars with no blue stars, I mean, star formation is not going on there, but it went on, 5 to 10 billion years ago, and these stars are just living out. Well, what about down here now? Let's look down there. All right, so this is a low mass, and it could be a long life, a very long life. How long? Some estimates range outwards of 1 trillion years for the smallest stars. They burn their energy, they just sip at it. So even though they have tiny masses, they use it so sparingly, they live a really long time. Up to 1 trillion years. Now typically you hear like 300 billion years, things like that, but a very, very long time compared to our sun. So just looking at the main sequence, you see all sorts of really interesting, useful data about stars that you could get by observing them. What else do you see? Well, some stars are not on the main sequence. They don't obey the rules we were talking about. One of the things that we find is a lot of stars up above the main sequence where we see red giants and red super giants, right? And I think you can get in the name why they look so bright. Even though they're dim, they fall into this class. They're quite dim stars. I'm sorry, they're not dim. They're quite cool stars. So even though they fall into this class of quite cool stars, they're not dim at all. They register as really bright. How can that be? Well, they're simply huge. They're so big, there's so much surface area giving off relatively small amounts of light per meter of surface area. There's just so much surface area. Some of these stars have swelled out past where Jupiter would be in our solar system. These are fantastically large stars. So they've expanded, and by expansion, they have cooled adiabatically because their atmosphere, the gas has expanded and cooled off, so they're reddish. They're vast reddish stars. We understand stars move off the main sequence into this. It's part of their end processes. The core of the star collapses because the nuclear reactions have died out, but the core collapse releases so much heat, adiabatically through compression, releases so much heat that it caused the outer envelope of the star to expand dramatically. And that's why the star expands, looks like it's getting cooler. The core is actually getting a lot hotter. The core is getting ready to potentially fuse the next set of elements along the line. We can fuse all of them up to iron. After that, things change. We'll talk about that later. After a star is all done with the red giant phase, when it's burned up everything it can burn up in its core, its mass now is going to determine what happens. How it dies is all based on the mass remaining in the star. Now, some stars blow off huge amounts of wind. That'll reduce their mass. Whatever mass is remaining is going to determine the fate of the star. Very often, stars with lower mass, or that have lowered the mass, there's a certain line, if you get to this lower mass, what's going to happen at the end of your life? You're going to become a white dwarf star. Now, this is weird matter. It's degenerate matter, where the electrons have been pushed so close to the protons. It's a really odd form of matter, and everything gets really close. A star like our sun is about 1 million miles across. It shrinks until it has the diameter, sit down for this, of the Earth. This tiny little remnant of the star. Now, in the end of its life, it's blown off most of its outer atmosphere. So really what we have is the core, the super dense core of a star. And you can imagine that's going to be incredibly hot. So where would that plot on this chart? It would come out of here and would plot in a region here called, white chalk for it, called white dwarf stars. Small, incredibly hot, and they're dying or dead, and they're simply now going to cool off. There's no more nuclear reactions going on. They're just going to cool off over large, vast amounts of time. So they go from white and eventually become red dwarfs and would eventually disappear. Right now, we see a lot of them as pretty bright objects. So this is what the Hertzsprung-Russell diagram does for us. It shows us how stars, not just how they're going to live their lives, but how they end their lives too. It's a good diagram to understand. Without it, we would not understand nearly as much as we do. We use this for a lot of things. When we see a cluster of stars, we plot them all on this, and we get an interesting result. Let me just show you the result of clusters, because this is how we understand a lot of astronomy. What we have is these stars, and I'll just plot a few of them. These stars that are mostly plotting along the main sequence. We have the dimmer stars. If a cluster is brand new, well, you'll go all the way up here, right? Because as you form stars, some of them will be brand new stars. But as the cluster ages, these stars die. And what you see, you'll see a turn-off point. The main sequence turn-off point. And that lets you know, because this cluster is important, all the stars formed at the same time in a cluster. So what its turn-off point is then shows you the age of the star cluster. And because you know it's all the same age, you really can start telling things about how stars live and die. Fascinating. If it has a turn-off point way down here, would it be older or younger? Well, if it has a turn-off point way down here, all these stars that live shorter lives have gone. So this is an aging cluster. And as it ages, the turn-off point climbs down. So that's one of the uses of the amazing Hertzsprung-Russell diagram. You heard it here. I hope it's all good. Take care of yourselves. Happy astronoming. Bye-bye.